Hello and welcome to this demonstration of Colostrum Monte Carlo, or CMC. My name is Jim Quigley. I'm the Managing Director of CAF Notes Consulting and the author of the Monte Carlo Simulator. Let's take a look at the program and see how it works. We'll begin with the Input screen. The program consists of two tabs, the Inputs and Results tabs, which you can see here in the lower left-hand corner of the screen. Below those tabs is the name of the current working file, and this will begin with default CMC file, which contains the basic information the program uses at the startup. Along the top of the screen are the available menu options, and the version number appears here in the lower right-hand corner of the screen. The Input tab contains the information needed to define and run the simulation. Just below the menu are three settings related to the simulation itself. The first is the AEA curve. The default is the exponential curve, which you can see plotted on the right-hand side of the screen. The form of the equation is also shown here. Several coefficients and variables in this equation influence the calculation of apparent efficiency of IgG absorption, or AEA. The calculated AEA is then used to estimate serum IgG concentration in the simulation. The number of simulations can be selected between 1 and 100,000 iterations, with a default of 10,000. 10,000 simulations is a reasonable number for most situations. We can also select 1, 2, or 3 colostrum feedings. The default is 2 feedings, and the number selected determines how much feeding information we must need to be entered. In the middle left-hand section of the screen, we enter information describing the calves and their feeding programs. The first row is the birth weight of Holstein calves. Here we're using a normal distribution with a mean of 41 kilos and a standard deviation of 5 kilos. Notice the minimum, maximum, and mode columns are shown in light gray. These values are not used with a normal distribution, so they're not available for entry. Plasma volume, expressed as a percent of body weight, is also initially defined using a normal distribution with a mean of 8.9% and a standard deviation of 2%. I'm going to change this to a normal truncated distribution. This allows me to specify the minimum and maximum biologically reasonable values, so the program doesn't get out of control selecting values that are out of biological reality. For ages at first and second feedings, I'm using a triangular distribution. Triangular distributions use a minimum, a maximum, and mode. The mode represents the most common value in the distribution. For the first feeding, for example, I'll use a minimum age of 1 hour and a maximum of 6 hours with a mode of 2 hours. Most calves will therefore be fed at about 2 hours of age, with progressively fewer calves being fed closer to the minimum and maximum ages. For liters fed, I'm assuming the calves are fed by esophageal tube, so I've used a fixed distribution for each feeding. Maternal colostrum IgG concentrations are currently set at 68 grams per liter. I'm going to change these to an average of 50 grams per liter and use a truncated distribution between 5 and 120 grams per liter. We'll make that change for both of the feedings, and we'll be ready to run the simulation. Once the inputs have been defined and we've selected the AEA curve, we're ready to run the simulation. There are 6 curves available, with the exponential being the default value. I'll click Run, and the CMC program will conduct 10,000 iterations, calculate serum IgG concentrations, and display the results on the Results tab. At the top of the Results tab, we see the simulated IgG distribution here, the chart here. The graph shows the percentage of calves across the range of serum IgG concentrations. In this example, we have approximately a normal distribution, with the largest percentage of calves being between about 23 and 27 grams of IgG per liter. The Monte Carlo results are summarized in the table in the top left. The first row is body weight. Our input mean was 41 kilos, and the simulation produced a mean of 41.1 kilos with a standard deviation of about 5 kilos. The table also shows the coefficient of variation, the median, and the 5th and 95th percentiles. Maternal colostrum IgG was set at an average of 50 grams per liter. The simulated result is slightly higher because truncating the distribution eliminated some of the lower values that would otherwise have been selected. As I move down the table, the graph at the bottom changes to show the simulated distribution of each variable. Here, for example, is the triangular distribution for age at first feeding. Most calves are fed at about 2 hours of age, with values extending from the minimum of 1 to the maximum at 6 hours. Liters fed in the first feeding was fixed at 3 hours, so all values were set at 3. Every calf received 3 liters of colostrum. This is also true for the second feeding. AEA at the first feeding was about 33%, with the 5th and 95th percentiles between 27 to 39. AEA at the second feeding was 20.7, with a range from 5th standard deviation, 5th percentile being 14.5%, and the 95th percentile at about 27. When I select serum IgG at the table, you'll notice that the bottom chart will be the same distribution as the top chart because we're now referencing the same information. Serum IgG concentration was 23.4 with a standard deviation of 7.8. The 5th and 95th percentiles are shown here. A few calves have serum IgG concentrations below 10 grams per liter, but relatively few fall into that category. The table in the middle of the screen is perhaps the most important part of the Results tab. It shows a proportion of calves with a consensus serum IgG categories, shown here. Lombard and colleagues recommended that fewer than 10% of calves in a herd have serum IgG concentrations less than 10 grams per liter. In this simulation, only 2.9% of calves, or 286 of the 10,000, had serum IgG concentrations less than 10. Another 22.8% of calves were between 10 and 17.9, and 35% were between 18 and 24.9, and about 39% had serum IgG concentrations equal to or greater than 25 grams per liter. In this example, therefore, the simulated calf population almost meets the requirements or recommendations proposed by Lombard and colleagues. The AEA calculations in the simulation can include adjustments for heat stress and pasteurization. These were not selected in this example, and we'll describe those in future videos. The effect of the intake of IgG is shown here. For every 100 grams of cumulative IgG intake, the AEA is adjusted down by 4.6%. More IgG consumed generally means that calves become less efficient. Once the simulation is complete, we can print a report that shows the results and print or save this for future use. The report includes the simulation inputs, the results, and the charts that were involved in the calculations. We can then return to the Input tab, make any changes, and repeat the simulation. And this allows us to evaluate a number of different options and feeding programs that show the effect of the feeding program on serum IgG concentrations and the proportions of calves in the various categories. Well, this gives you a brief introduction to Colostrum Monte Carlo. There is much more that we can do with the program, but this should give you a good start on how to set up and run a simulation. Thanks for watching, and see you soon.